In this video, we are going to be doing an example where we're going to use Mohr Circle to compute the principal stresses and maximum in-plane shear stresses for the element shown here. And just to make sure we know what we're looking at, we have a stress element that is subject to a tensile stress in the vertical direction, as well as a compressive stress in the horizontal direction. And then we have an applied shear stress in its positive sense. So just like always, I like to summarize what we know. We know sigma x is negative 20 megapascals. Sigma y is a positive 90 megapascals. And then the shear stress is in its positive sense, seen by the figure. So that would be a positive 60 megapascals. So just like in our previous examples with Mohr Circle, we are going to start by calculating the center of the circle. So the center is always given by sigma average comma 0. And so for sigma average, we're going to have sigma x plus sigma y over 2 comma 0. But be careful, sigma x is negative here, so you'll end up with a 35 megapascal sigma average comma 0. So that's negative 20 plus 90 is positive 70 over 2. That's where we get the positive 35. Okay, next we need to define point A in our Mohr circle, that point A. And as we've discussed already, that's defined by your local axes in the same orientations as the global axes. So the point A would be sigma x prime comma tau x prime y prime, which will end up being sigma x comma tau x y. Okay, and as we've mentioned in a previous video, that would always be the case when you're defining point A, so long as you define your local axes corresponding with the global axes for point A. So when we punch this through, it's pretty simple. Negative 20 megapascals comma positive 60 megapascals. And then we're going to define a point G. So again, sigma x prime comma tau x prime y prime. Often when we define point G, we have rotated our local axes 90 degrees counterclockwise. So the element and the global axes and all the stresses stay in their given orientations. It's just the local axes have rotated 90 degrees counterclockwise. When that happens, the sigma x prime value corresponds with sigma y, and then the tau x prime y prime value will correspond with a negative tau xy. So if you can't see that, draw it out. That's okay. Draw the element out and show the local axes rotated 90 degrees counterclockwise, and then you'll be able to more clearly see this. So point G would be 90 megapascals and then negative 60 megapascals for the shear stress component. So now we're ready to draw the Mohr circle. So I'm going to scroll down a bit to page 2. And I'm going to try to draw this as best as I can, not being much of an artist. I have tau going up as positive. Okay, and I have sigma going to the right as positive. You want to put those units on your axes always. So let's put in point A, okay? Point A is gonna, well, actually, I tell you what, before we put in point A, how about we scale this off to some reasonable values? That way, we'll hopefully be able to then more easily plot our points. So I'm gonna do that first. I'm gonna maybe put this over here as 120 megapascals. Halfway through would be 60, and then halfway between that would be 90, and then we've got 30 right here. So I am doing a bit of eyeballing here. You want to draw this as much to scale as possible when you're doing your homework. So that's 30 here, and we're gonna have 1, 2, 3, 4, 5, probably 60 here, a negative 30, and a negative 60. Okay, so let's go ahead and now we can more easily define our points. So point A was, if we look back up here, point A was negative 20 comma 60. So we're going to go down negative 20, so that's to the left, and then up 60. So that's going to be about right here as point A, okay? And then point G was 90 comma negative 60. So to the right 90 and then down negative 60. So that's going to be right here. And remember, as we've mentioned in all of our previous videos on this topic, AG is a diametric line. So AG defines a diameter of the circle. We already know where the center is. That's 35 comma 0. So if we want to put the 35 comma 0 in, that's probably going to be right about here. On your homework again, we can you should draw this to scale. All right, so we're going to pass a straight line through here, and I'm already veering off to where it's not looking very straight. Try to draw this as best as possible. There we go. Okay, so we have our center, our A, our G, and our diameter drawn, and now we can swing this around and draw the circle. As you can see, based on how I drew my vertical axis, we're gonna probably exceed where the vertical axis is. So we just need to just keep that in mind. Again, on an assignment, you want to draw this much better than I clearly have here. So we're gonna swing this around and try to make as nice of a circle as possible. And this isn't too bad. Okay, and then gonna kind of clean this up a little bit. All right, that's probably, let's see if I can make this a little better up here in this region. Looks a little wonky there. All right, I don't know if that's much better or not, but that's probably as best as I'm going to be able to get it. So, so we have our circle here, and we need to make sure we know that where the circle intersects the horizontal axis, those are our principal stresses. So the larger value, the larger intercept is sigma 1, and the smaller intercept is sigma 2. And you know, the previous couple of examples, we were interested in the stresses on a particular plane. In this example, we are interested in specifically the principal stresses, okay? The principal stresses. So we need to geometrically figure out how to get these. So we pretty much have everything we need. The first thing we should try to get is the radius, okay? So here is a radial line. All right, we'll call that R for radius. We could get the radius up here as well. This is also the radius. So we could use either A or G to help us get the radius. So here's what I'm going to do. I'm going to use point G to help me get my radius. So do I know where point G is? Absolutely. I plotted it. Here it is. And then the great thing about knowing the center and where point G is that we can build this right triangle right here, okay? So we got this right triangle that we can definitely make good use of in terms of getting some information. So here's what I'm going to do. I'm going to use the Pythagorean Theorem, which, as you should know, the Pythagorean Theorem turns out to just be the distance formula as well. So here's what I'm going to do. I'm going to say square root, and I'm going to look at my horizontal dimension first. This horizontal dimension right here is 90 minus 35, okay? You see that? It's this 90 minus the center point, 35, gives me this length. So that's going to be my first term in my distance formula or Pythagorean theorem, however you want to think about it. 90 megapascals minus 35 megapascals, quantity squared. And then the next piece I need is this vertical dimension right here, which that is just negative tau xy, right? That's just the 60. That's how we defined point G there. So I'm going to say plus 60 megapascals, quantity squared, and we're just doing a triangle operation here. So when I punch this through, I get a radius value of 81.4 megapascals. Okay, now remember it's a circle. Radius is constant as you spin around this circle, which means that where else do we have a radius? Well, we know that from the center all the way to our sigma 1, guess what? That is the same radius value, isn't it? So what can we easily look at what sigma 1 is? Absolutely. We say sigma 1 is the center value, okay, the center coordinate plus the radius length, okay? So all we have, the center coordinate was defined by sigma average, so we say sigma average plus the radius, and that's 35 megapascals plus the radius, 81.4 megapascals, and we'll get a sigma 1 value of 116.4 megapascals. And sure enough, if you drew this to scale, you would see that this point right here is just to the left of 120, so that would be about 116.4. Okay, so it's important to draw these to scale so you can see the shape and you can visualize the numerical values. What about sigma 2, the minor principal stress? Well, we're going to do something similar. Remember, this is a radial line from the center all the way to sigma 2 as well. This is also a radial line right here. So how can I get sigma 2? Well, I'm going to say the center coordinate, 35 megapascals, minus the radius, and that's going to put me right over here, okay? So here we go. We're going to say sigma average minus the radius, so that's 35 megapascals minus 81.4 megapascals, and I get a negative 46.4 megapascals as sigma 2. So those are two of our answers right there. They asked for the principal stresses, and then the problem also asked for the maximum in-plane shear stress. So check this out. Tau max happens where? It happens at the very top of your circle, or it also, you could think of it as it happening at the very bottom of your circle. So right here, I'm gonna give this value right here as tau max, and that's the positive tau max, and then this value over here would be the negative tau max. So we could say tau max equals plus and minus, and guess what? It's a circle, so what does that value equal to? Just the radius. So that equals 81 plus and minus 81.4 megapascals, and that is also part of the answer. So one of the great things about the Mohr circle is tau max is the radius, okay? It is the radius. So if you wanted to, you could confirm that these were your values using the principal stress equations. You could double check yourself with those just to make sure you're getting the right values. But that's it. Pretty simple to get principal stresses and maximum shear stress when you're using a Mohr circle.